So welcome everyone to the webinar Resource Providers for Science Gateways. I'm Sandra Gesing. It's my pleasure to moderate this session. So I'm one of the co-PIs of SGX3 for community engagement, and I will be strict this time. So we have a full fantastic agenda with 9 talks. Every speaker has 5 minutes. If they go over the 5 minutes, they get a boat horn to hear, and I will mute them afterwards if they still continue. With questions, please wait until the end that every speaker has a chance to get their 5 minutes. You can put them in the chat. We try to answer everything in the last 10 minutes. And with that, I would ask the first speaker, Mike Zentner. He will talk about science gateways, to share his slides and start.
Can you see my slides okay? Yeah, okay, good. All right, as Sandra said, thanks for taking the time today to attend the webinar, and hopefully you'll learn something interesting about access providers and how they might use science gateways. I'm the PI of the SGX3 Center Excellence. And these things that helped people who didn't have the skills to jump over this skills fence of being able to access HPC resources, to do it by opening a little doorway with a web portal that would let them through that and be able to use those resources even though they may not have those skills. Now, why a resource provider might care about that, if you look a little bit at some older historical exceed data, you can see that a large fraction of the gateway usage, or a large fraction of exceed resource usage, came from gateways. And they're an important way to do that. And why gateway people care about resources is they need compute resources to run these things. But I'd like to encourage you to take a slightly different view of science gateways as web-based platforms for making connections. And yes, one of those connections is between scientific software and supercomputers, but as soon as you started doing this, suddenly large audiences saw these resources that were available and wanted to use them, even though they didn't create them. And so they connect large audiences. They also connect and democratize access to expensive instruments. And when you talk about expensive instruments, you've got to start talking about data. When you talk about AI, you've got to start talking about data, and gateways facilitate data-centric computation sometimes. And we shouldn't forget that they connect us to each other as well. They connect us to collaborators. You might say, well, how big is this science gateway field? This is an example of the NanoHub Science Gateway over several 24-hour periods, showing just how much usage around the world a gateway can have. They make a scholarly impact. The Cypress Science Gateway has supported almost 10,000 publications that cite it, so that's a pretty good number. They support collaboration. Out of 2,700 citations looked at on NanoHub, you can see co-authorship networks emerging in collaborative groups. Way estimates that it would take $16 billion to reproduce the contents of it. So hopefully, as you think about this, you think about gateways as engines to make the efforts of a few available to the many through simple to use interfaces. They democratize access. What you might not think about is they're also a place to talk about sustainability, where many investigators in a common scientific area might band together to sustain their efforts that individually they couldn't do. So if we convince ourselves that science gateways are a good idea for access resource providers and people that want to use them, the next thing that happens is people usually say, well, how hard can it be? It's just a website, I'll go build one. And a year later, you find out it was pretty hard. We are created to help with that process. So the Center of Excellence, you can think about as an advisory and community building entity. And a software institute is really a full service consulting organization that we have both of these things. The Center of Excellence provides technology advice, developing architectures and gap analysis. We provide intern placement. We do provide annual sustainability training for those that want to learn more about that. We've got an annual conference this year taking place in late October in Pittsburgh. I hope some of you will come and see us there. It's a great time. We help people find partners that either want to build gateways together or join existing gateways, and we do provide user experience consulting as well. On the Institute side, we are a full outsourcer. We provide development support. We can augment a software team, or we can act completely as an outsourced team to help connect with gateways to these access resources. We even operate gateways for people who don't want the hassle of operating a gateway. And for those that went through sustainability training, we can help provide in-depth sustainability analysis and development. We've been doing this for about 7 years now. We've had a large number of engagements. And this storybook of these engagements is available on our website. I would encourage anybody that's interested to contact us, and we'll make sure you have a link to it if you can't find it. But I'd like to point out that the financial impact as well. When we interviewed clients after their engagement with us, we found that by working with us, they've been able to accomplish technical goals about 7 times faster than they would have done themselves. With that, I'll stop and turn it over to the resource providers.
Thank you so much, Mike. And nobody did hear the boat horn, so he kept it 5 seconds in the time. Very good. Here we are. That is my stopwatch. So welcome to the next speaker. So Arman Pazouki will talk about Anvil.
Thank you, Sandra. Let me share my screen. And let's see. All right, do you see my screen? Awesome. So I'm Arman Pazouki. I'm talking on behalf of the Anvil team. Anvil is a resource supported at Purdue University. Very broad perspective of Anvil. It features 1,000 compute nodes with AMD Gen 3 EPYC processors, 5.1 petaflop peak performance. It has 64 NVIDIA A100 GPUs, 32 large memory nodes, 10 petabyte of storage, including flash storage and also object storage. And also, I think one of the unique features that I would like to highlight more for this community is the composable subsystems that is supported by 8 large memory node and 4 A100 GPUs that also has MIG to have further splicing. Type of use cases, traditional HPC and HTC, same as probably most, or if not all other providers. A couple of unique features are biocontainers that have been developed in-house, almost 700 of them to support life science applications, and Hypershell to support the workflow automation for HTC. One of the other missions that we have is to support non-traditional HPC domains using Open on Demand and Pinlink. Considering the composable subsystems, one of the use cases is databases, gateways, cloud integration, and so on. And also considering the GPUs, it's also great for AI and ML applications. And there are several layers of application support that is provided to support AI from the foundation to the framework. The one unique feature I would like to highlight further for the gateway community, in addition to supporting resources for the existing gateways, Anvil is also great in terms of composable subsystems, which are cloud-style, highly customizable subsystems that users can pick CPU, GPU, memory, disk, network to host their gateways. They are designed for persistent edge services and hosting gateways for long-running scalable data processing. It's backed by Ceph-based block object storage, and also it supports automatic publishing of domains, as you can see in the DNSs provided there. It can be accessed via Rancher GUI as well as a standard Kubernetes CLI tools. Some of the considerations for using composable subsystems and also using Anvil for the gateways, I think from the gateway submission to the Anvil, basically there are individual QSs per allocation. They are supported by community allocations, and they are pretty generous since they are individual QSs. They can be also customized based on the needs. On the composable side, the only limitation is the resources that are available, but also there are plans in place to dynamically add resources as the resources are exhausted. Some of the application cases are listed here. Anvil has provided iGuide project funded by NSF under PI Wang. It's basically, and a multi-institutional partnership focusing on sustainability, resilience, and providing access to cutting-edge geospatial data capabilities. There is GeoEDF, which is NSF CSSI project under PI Carol Song. It's a framework for designing and executing a spatial research workflows. And finally, NanoHub under Director Klimek. It's a Hub Zero-based gateway for material science research and education. And that concludes my talk. And I'm glad I didn't hear the hard stopping buzz.
Very good. You kept it totally in time, so thank you very much. So the next talk will be from Sergiu Sanielevici. I should know it after all these years.
This was very good, but I think, Arman, can you stop sharing? Okay. Okay.
Okay. So yeah, for the next speakers, then maybe when you're at the end of the talk, start directly to unshare or not share anymore, so that the next speaker can come up with their slides.
Can you see it now?
Yes, it looks good.
Okay, very good. So thank you for the invitation. I'm Sergiu Sanielevici of the Pittsburgh Supercomputing Center. I'm the principal investigator of the Bridges2 project. And let me go to the slideshow. Okay, so here's what a brief overview of the overview. So this is Bridges2 is a project of the Pittsburgh Supercomputing Center, and we've been around since 1986. This is a quick one slide summary of what we've been up to here since that time. Bridges2 is a project awarded under category 1 of OSC projects in way back in 2019. And we've been in production since 21. We had a slight delay because of the pandemic. And we designed it specifically for convergence between HPC, AI, big data, and just with a lot of flexibility in mind. So we have a variety of hardware nodes. We have AMD nodes in two flavors, regular memory and large memory. Then we have some Intel nodes with really large memory, 4 terabytes each, but not many of them. And then we have 2 generations of GPUs. And then we have service nodes and data transfer nodes, which we can use to accommodate the needs of things such as science gateways. Software-wise, we prioritize flexibility and ease of use. So we have all kinds of things. If we don't have what we need, we can, bring it in. So again, it's very multivalent and can do a lot of things. And we love to work with folks to make sure we customize and try to accommodate what they need. We are active and popular resource provider in access. So I include on the right there a pie chart of recent allocations from XDMod, which is the place in access that measures usage and things like that. So again, we're not the huge resource, but we are pretty widely requested and used. Also in terms of Bridges staff, we contribute to several access initiatives. As an RP, we're pretty active there. In terms of science gateways, we are, again, quite a popular provider in terms of number of grants and usage. The largest gateways right now are on Bridges regular memory nodes, and you see them there. So it's CMS, GridChem, ChemCompute, and Galaxy. Those are the top consumers of our resources. And what is of interest to gateway developers and to you guys, if you don't use us already, if you're interested, we'd love to talk to you. As we saw, we enable complex and heterogeneous work and data flows, both within the system and also within the WAN. We've been supporting Science Gateway since they got started in 2006 on various systems. We've had a continuous partnership with SGCI and now with SGX3. And what we like to do is we like to have like individual discussions with folks who are interested in developing hosting plans, because, you know, every gateway is different. And obviously, you know, you're being advised by, you can get advice from SGCI, but we would like to find a solution that works best for you guys. So thank you for your attention. And if you have follow-up on this overview, you can send email to me. And more generally, you can find us at help@psc.edu. So thank you very much.
Thanks, Sergiu. And we are taking questions at the end of all talks. Please unshare your slides, your screen.
I'm trying to do that. Where do I do that?
If you go on the green button, share screen, maybe, or something in the middle.
Yeah, I don't see that anymore.
No, it should be on the top.
Oh, here's a thing. And
Great.
okay.
Thank you, Sergiu. So the next talk will be about Delta and is presented by Bode.
All right, thank you, everyone. I'm going to do a quick introduction to Delta. So as with the previous systems, Delta is also one that was funded by the NSF Category 1 program. We went into production operation September of last year, so relatively recently. Also a bit of a delay in production due to the pandemic. So we're a little later than we'd like to be, but we are in production and remain still ramping up things. So this is kind of an overview of the hardware on the system. We're a little different than the other providers in that many of the other providers have larger CPU partitions with a modest GPU component. Our intention all along has been to provide a very large GPU capability. So we end up with over 800 GPUs total within our system. That of course means that the total node count is lower than the other systems of similar cost. So we have a bit of a mixed environment that includes multiple types of GPUs as well as CPU nodes in our system. All the nodes use the same CPU cores. They're AMD Milan 64-core processors. The CPU only nodes have dual socket systems, so 128 cores, modest memory. Then we have single socket CPUs in the most of the GPU nodes, with 100 nodes that are quad A100s, 100 nodes that are quad A40s, which are a version of the Ampere silicon that does not have much double precision capability, but still has pretty good 32-bit and machine learning sorts of capabilities, and are a bit cheaper. We also have 5 large memory nodes that have 8 A100 GPUs. Those have 2 terabytes of memory apiece, along with an 8-way AMD MI100 node for those that might like to try an AMD GPU. I think as far as we know, that's the only allocated AMD GPU system in the Access portfolio. This is backed up with 10 petabytes of total storage, of which 3 petabytes are in a flash storage environment. Overall performance is on the order of about 10 petaflops of double precision capability, or 100 petaflops single precision, 200 petaflops of 16-bit tensor core sorts of precision. So a very capable system, and particularly of interest for those that have applications looking to use GPUs. When you're looking to do allocations on Delta, we have 3 resource types mostly self-explanatory. The Delta CPU is for core hours on the CPU only nodes. It does not apply to the CPU usage on GPU nodes. Any CPU usage on the GPU nodes will be charged as a fraction of a GPU hour sort of thing. So the other one is main one is Delta GPU, which is A100 GPU hours, with a 40 hours being charged as a discount to the A100 hour in that same allocation type. And then if you need more than the default storage allocations for our Scratch file system, you can request Delta storage as well. We do have a software environment that's we think is fairly rich with a good support for a lot of traditional simulation codes as well as AI codes. We have a mix of a lot of different compiler types to support traditional sorts of things, including both AMD ROCm and NVIDIA HPC SDKs. We're working on integrating the Cray program environment as well for those that might want to use that. We do have full container support, so we do fully support containers from both NVIDIA and AMD, which are reasonably popular for some apps, including some AI sorts of things like TensorFlow and PyTorch. And we are working to develop a service for persistent services for users. We do have a lot of Python codes already installed on there. We do install everything we can with SPAC to provide a pretty rich environment, and are still enlarging that environment as we get new requests. So if you don't have what you need and can be installed by SPAC, please do so. We do have Open on Demand as well on there, as with others for that. And finally, we do have our own gateway, which we're partnering with SGCI folks to deploy. We do want to support gateways as first-rate things. So if you're interested, please let us know. We have a couple that are already partnering with, and we would look forward to working with you as well. All right.
Thank you so much. You made it on 1 second. Very impressive. 4 minutes and 95 seconds. So the next speaker is Amit Majumdar, and he will talk about, let me look at the agenda again, Expanse. Welcome, Amit.
Okay, thank you. Welcome, everybody. Hi, I'm Amit Majumdar, and this talk is on behalf of the big Expanse team at SDSC. So Expanse is also a Category 1 award, and we have...
we don't see your screen yet. Did you? So we see a black screen.
You're not seeing it?
I can see a screen.
I see it.
I can see as well.
It might be your internet, Sandra.
Okay, yeah. Sorry for
Okay.
interrupting. I give you 10 seconds more.
Okay. Yeah, so initially we had 13 scalable units, which AMD EPIC processors, 228 socket CPUs, 256 GB of memory. And then we had, we still have GPU nodes with V100, but then over the time we added 2 path racks, which has the Milan-based compute nodes, and another is SDSC funded rack. But it has a data-centric architecture with 12 petabyte of storage, and the main focus is long tail of science, which fits very well with the science gateways and the innovative operations, again, composable system, high throughput computing, science gateways, cloud bursting, and I'll talk about some of those. Again, the focus is for long tail of science, and this is following the tradition of long tail at SDSC for many, through many processors of machines like Trestles, Gordon, Comet, Expanse. And the single node and single core jobs are for first-class citizens, and there is shared node scheduling on this large core count and 128 core AMD EPIC processors, and there's a node local SSD. And then we limit the job site to fit inside a rack, so that inside a rack there is full bisection bandwidth, but we fix the max job size to 4096. And the machine is a little bit under allocated. That helps with gateways as well as interactive jobs. And obviously gateways is one of the access modalities, along with Open on Demand for interactive use, and Open Science Grid Portal, Jupyter Notebook, and obviously SARM and Kubernetes orchestration. And so some of the innovations is, again, similar to the Anvil project. We have the cloud bursting. So we demonstrated cloud bursting from 2 science gateways. Cypress is a Phylogenetic Science Gateway and NSG is the Neuroscience Gateway. For both of them, we demonstrated Science Gateway jobs going to AWS. And we have composable systems, making it part of a big CI ecosystem. So edge computing of wildfire workflow, which is from Altintas, and as well as the two-path racks are integrated through Kubernetes. We have a special program called HPC at MSI, where out of the discretionary allocation, the director, which is Mike Norman, is the PI of the Expanse machine has, we give allocation through a very simple allocation process, like one-page write-up to minority serving institutions, so they can gain experience using research and then move on to access allocated PIs. And and we have various support and allocation process for science gateways. I mentioned some of them, and we're looking forward to collaborating with anyone who is interested in using any of these or science gateways. So some of the highlights of science gateways: the allocation limit for a single PI is 15 million, whereas for a science gateway PI is double, 30 million. And as I mentioned, the job management, there is shared node jobs and every partitions, the compute node, GPU shared large memory. And so science gateway jobs, which have lots of jobs, can take advantage of these shared nodes. And then system, as I mentioned, is under allocated bit for good job turnaround. We can set QoS for gateways. There are some of these gateways, like Cypress has over 20,000 users. I think ITAS, or protein structure prediction, has over 20,000 users. So they have lots of jobs. We can set the QoS accordingly. And then we have external storage, which can be mounted both on the Science Gateway web servers and Expanse. And some of the Science Gateways are taking advantage of that. It's very useful for Science Gateway architecture. We support 19 highly impactful gateways. I mentioned ITAS, Cypress for phylogenetics, Cosmic 2 is for cryo-EM, and tens of thousands of users are using it. I'll just highlight one of the gateways. And again, all of the other gateways are getting similar kind of impact. So Cypress Expanse is its main compute resource. In October 2020, over 27,000 users from almost 100 countries, over 750,000 jobs, close to 50 million core hours and 300,000 GPU hours, over 1,800 publications. I think Mike Zentner mentioned Cypress probably has close to 10,000 publications over its lifetime, many discoveries, and publications are in prestigious journals like Science and Nature, and similar impact on other science gateways also. Thank you.
Thank you very much, Amit. So the next talk will be by Jeremy Fischer about Jetstream 2.
Greetings. Can everybody see my screen okay?
Yes.
Excellent. All righty. So Jetstream 2 is a little bit of a different resource from what we've heard about so far. Jetstream 2 is a true cloud resource. It is a NSF-funded production cloud environment, and we're kind of building on the success of our previous cloud, Jetstream 1. On the previous system, we had 63 gateways over the lifespan, indirectly supporting about 180,000 users. One of the things we really pride ourselves on is that as a cloud resource, we can kind of do our upgrades and maintenance in a rolling mechanism. So over the time of operation, we had a total uptime of 99.9967, where we were operating even if it was in a somewhat reduced capacity. So we try to keep part of the cloud up at all times so we can keep doing our maintenance work in the background and keep everybody working. A little bit of a look at our features. So we are AMD EPYC 3rd generation Milans. We have 400 nodes for that, 90 GPU nodes with 4 A100s each, so 360 GPUs, and then 32 large memory nodes with up to 1 terabyte of RAM each. There are also 4 regional clouds in addition to the IU primary cloud. Those are available by invitation request, and those are represented by Arizona State, Cornell, Hawaii, and TAC. Our default storage is NVMe. We have large data set storage available on hard drives. We also provide a file system as a service for sharing between VMs, which is something that Jetstream 1 users had really asked for. Load balancing as a service was recently deployed. And then we also use a shared application store similar to HPC, where we have a bunch of common applications available to VMs basically as soon as they boot. Some features we have are federated Jupyter hubs, virtual clusters using Slurm, as well as other forms of orchestration. And then we have support for commercial cloud integration and funding with Jetstream 2 that's coming this year as additional part of our project. Hello. There we go. So gateway use of Jetstream 2 happens in a lot of ways. So of course we have the gateway web hosting. Several gateways have been mentioned on here before using some of the other resources. Chem Compute, for example, is actually housed on Jetstream 2 as the front end portion of the show and the database. And then computes elsewhere have data sets and database housing. Integrated Jupyter hubs, and then interactive computing is a big part of our use case. So we have a lot of folks that either are doing prototyping or they're using GUI applications or things that have more of an interactive use case. And then again, elastic virtual clusters using Slurm, and those are available from a push button interface through our Exosphere interface. Some usage considerations. As I noted, we do not schedule downtime for upgrades. We do that in a live rolling fashion. We just did our stats for our recent NSF review, and from our production date in September through the end of last quarter, we had a 99.87% uptime rate. Persistent IP addresses for the lifetime of an allocation. So gateways can stay on the same IP for the whole time. There are no runtime limits. You can continue running as long as there's an active allocation with SUs. There are no allocation limits that way. If you can justify it, you can have it. And the same for instance core and RAM limits. We're pretty flexible with that. Most allocations never need to exceed 100 cores or 200 cores, but we have some that are using several thousand cores for different flexible and elastic workloads. So that is available. We do have some gateways that are using elastic clusters, and we'll go from using just a gateway service to using several hundred or 1,000 cores at a time. And then storage allocations, reasonably generous for cloud. So we default with 1 terabyte and up to 50 terabyte in volume shared or object storage. Presently, we have 56 gateways using Jetstream 2. The gateway users per allocation range from single digits to over 60,000. And I just kind of put some logos of some of the larger gateways or common gateways on here that are using Jetstream 2. And that gets me in before the time.
Absolutely. Thank you so much. Our speakers are so well behaved. I love it. So the next speaker is Eva Siegmann, and she will talk about Okami.
SGX3 system, which means it's a testbed system. We are located at Stony Brook University, and we're operating it in cooperation with a team at the University of Buffalo. This is what Okami looks like. It's probably much smaller than all the other systems you saw before. It has 176 compute nodes. But the special thing here is that those are Fujitsu A64FX nodes. So they're not very common, at least in most supercomputers or clusters. 48 cores per node. And one specific thing I want to highlight here is the memory of 32 gigabyte at 1 terabyte per second. So high bandwidth memory. Other than that, pretty standard Lustre file system, around 800 terabyte storage. Summing up all this together, we have around 1.5 million node hours per year that we can provide. And you might think, what was the motivation to get this testbed? And that was Fugaku. I won't say a lot about that because I assume everybody at least has heard of Fugaku. Fugaku is located in Japan, and for the last 2 years has been the fastest machine worldwide. And the interesting thing here is that it was not only the fastest machine worldwide, but it scored #1 in all 5 major benchmarks. So the system is very, very fast. It's well suited for a wide range of application, and simultaneously it's very power efficient. So this was the motivation to get a similar system at a smaller scale, also in the US, funded by NSF, and that is what Okami is. The processor we are talking about is a Fujitsu ARM-based processor. It supports high calculation performance and low power consumption. And the power consumption is actually very interesting. It's less than 2 times less than conventional chips. It's very, very low. We have high bandwidth memory and support for scalable vector extension with a vector length of 512 bit. The chip has 48 cores in total, divided into 4 CMGs or core memory groups. The processor, we worked with a lot of users so far, mainly in testbed mode. We are currently transitioning to, and the applications which perform well on the system and are a good fit are well vectorized, well threaded, and use for less than 32 gigabyte per node. And while being well vectorized and well threaded, the compiler can actually do a lot of that work for you. So it's important to just port the application to A64FX and set some specific flags. And we have quite some experience already with how to get things running and get things running fast. The restriction of 32 gigabyte per node might sound a bit in the Exceed network within a year, and they saw that 86% of all nodes of all jobs, used less than this 32 gigabyte per node. So the majority of jobs are actually fine on this processor. We are a testbed, and we just recently, like half a year ago, or a bit more than half a year ago, joined the Access network. So we are pretty new here, and we want to interact with you. We want to interact with the community. We don't yet have any science gateways on the system. We want to change that. So we do have personal support to port things and to set up things and to help you get stuff running. So if you're interested, reach out to us. We can definitely help you doing that. We have the support. We can also create, I don't know what exactly you need, but something like dedicated queues or specific storage, things like that, whatever is useful for you. If you look at the conversion factor, it seems high, but that's because whole node is allocated to a job. We don't do node sharing, and we are actually currently in the process of adjusting the conversion factor, so making SUs on the system like cheaper. And that's because we are now transitioning into production phase, and we want to fully utilize the system, want to go away from testbed system. Okay, feel free to reach out to me if you have any questions. Thanks.
Thank you. So the next talk will be by Christina, Koch, and about Open Science Pool, Open Science OSG services for Gateway. Take it away.
Thanks, Sandra. Hi, everyone. My name is Christina Koch. I'm the lead for the research facilitation team for the OSG, and happy to be here today. Start my timer. So I have something going on the side. So yeah, I'm here to talk about OSG services. These are funded by a couple sources, but mainly by the NSF award, the Partnership to Advance Throughput Computing. And the principal one is what we call the Open Science Pool, or OS Pool, which is a national resource of computing capacity contributed by all the little green stars that you see on the screen here, into sort of a single pool of computing capacity that's really well suited for high throughput workloads, which I'll talk about in a second. Some important features of the system are that it's free. It doesn't even need an allocation, although you can get an allocation for it through Access. We have lots and lots of cores, CPUs, we have GPUs, and then an additional service that we run is providing an access point, which is kind of our term for a login node or a head node that allows you to submit jobs to this pool of resources. On that access point, you can manage hundreds or thousands of individual jobs. And then baked into all of this is a data distribution network called the Open Science Data Federation. And that sort of comes with baked into both of these available services. This access point technology by default submits to the OS pool, but it's also possible to kind of bring allocations and submit jobs from our access point to other access resources, for example. And so if that's something that's useful for you, it's possible. Our specialty is in high throughput computing. which we define as execution of many independent self-contained tasks. There are a lot of research examples that fall into this category. Anything where you need to run essentially the same thing, but with slight variation many, many times. That can be bioinformatics, statistics, physics, or other kinds of simulations where you want to test a lot of parameters, or analyzing a bunch of different independent data files. So features of HT Condor, which is the sort of job management orchestration system that we're using, and these OSG services that might be used for gateways, is a Python API that you can use to programmatically interact with the queue, being able to easily submit and have thousands of jobs running at once, being able to bring your own allocation with you if you want to use capacity from different sources, all from one place, using data from a bunch of different sources, and S3, web services. It's all possible to do all that from Condor job submission. We have the Open Science Data Federation for serving data. We have workflow tools built on top of HT Condor, and you can use containers. And if you were building a gateway on OSG services, I would strongly recommend that you do so. There's definitely some, beyond sort of all the good things, some considerations for using a gateway on OSG service would be to talk to us to make sure we have the right infrastructure or account set up, recognizing that our resources are geographically distributed. And so there's no shared file system. We can't handle data that's more than 10 to 15 gigabytes. There's some heterogeneity in our resources. A lot of these things are, we can work around. So I think talk to us if you need something slightly different. Also, by default, our resources are available to US-based researchers and their collaborators. Again, talk to us if you're not sure if you fall into that category. We don't have any like big working gateways on OSG services right now, but the Science Gateway team built a little prototype for the Event Horizon Telescope project that you can check out if you want after this. And this is how to contact us, support@osghdc.org, or this link will take you to kind of a user-facing page about our services. Thanks.
Thank you so much, Christina. And sorry for saying your last name very German. I said Koch. Yeah. So I will remember it's Koch. Yes, I will do. So the next speaker is then Stanzione, and he talks about Stampede2.
Can you hear me at all at this point?
Yes, we can hear you, and we can see slides.
I'm on a cell phone on a highway in the UK, so I'm trying to get to my I'm not driving, so that is safe. But yeah, actually, I'll talk to you about a couple of the systems we have, and I just have 3 slides, so I actually stay within my 5 minutes because everybody knows I can't really do that. But yes, we have Stampede2, which is the one I'm officially supposed to talk about, but it's worth noting that Stampede2 is getting kind of long in the tooth. It went online in production in June of 2017, which means we've just finished 6 full years, or we're about to finish 6 full years of production, and heading for the 7th. We are about to start shutting parts of it down, which makes it not necessarily the best gateway target for some of them, which is why I want to talk about other systems, but it is about 6,000 nodes, about 400,000 cores. It was number 10 in the world when it went online. It's a mix of all Intel chips at this point. Knights Landings from way back when, the 2016 chips, Skylake Xeons and Ice Lake Xeons. About 4,000 of the nodes are KNLs. They're actually going away in July. Those actually predated the start of production, so they're almost 7 years old at this point. We're going to keep the remainder online until there's something to replace it, which I can't quite talk about yet, but I will be able to talk about it by perk. But just suffice to say, there will be, not at this scale, but there will be a Stampede3 that will be available. But over its lifespan, you know, we've had about 20,000 different people run jobs on Stampede. We've had 11 million jobs, 330 million node hours, about 15 billion core hours. Almost all of that was exceed and now access allocated. We also have Frontera available that will go for a few more years. That is 8,000 nodes. It's 450,000 cores. It's about 40 petaflops of, again, straight up Intel CPU is 40 petaflops. It was number 5 in the world in 2019. It should fall out of the top 20 when I get to ISC in Germany on Monday. It also has a couple of GPU subsystems built around both A100s and RTX 5000s from the Volta generation. It really focuses on the capability users more than the smaller users, but there are still big throughput jobs on there, a fair amount of, large ensembles. But, we put about 200 projects on Frontera, whereas we put about 3,000 on Stampede. The reason being we want to give everybody who's on Frontera a lot more time to do whatever it is they're doing. So it's sort of 250,000 at the low end to 5 million node hours at 60 cores per node. So like 300 million node hours per user at the high end. It does mostly run parallel jobs. There are actually hundreds of thousands of throughput jobs every year that are single node. But 97% of the cycles go to jobs that are above 160 cores and about 25% to jobs over 30,000 cores. And it actually, following in the footsteps of Blue Waters, is outside the access process for allocations. We may be able to integrate it in the next couple of years, but for now you go to the Frontera user portal to request time on that machine. There's a number of features that both machines and our various storage systems have for gateways that support these things. We've also had a long partnership with what is now SGX, and we're part of the original team, going back to when Nancy started this with Sandra, 10 years ago now. But both of those machines that I mentioned, and both our archive system and our online disk storage system, Ranch and Corral, support access via REST APIs. We use one called TAPIS, which is an acronym for TAC APIs, but is also a Longhorn Bull, which fits well with UT Austin in Greek mythology. So, but they include support for data transfer, job submission, application registration, authentication, etc., as well as a subsystem of it called Abaco that does serverless computing like FunkX or the Amazon serverless. You just need to run a function through a web service on one of the machines. But these are all REST APIs. They also have Python wrappers. It's sort of the most common way to build gateway support, but there are others. We do natively support containers now through Aptainer, formerly Singularity. The old versions of Singularity.
30 seconds.
What's that?
30 seconds.
Yes, I'll check into it. But we have Condor support and OSG support, as Christina mentioned. We have Globus services like FunkX. We have virtual login nodes, and separate Kubernetes machines when you need interactive sessions. So last thing, are there gateways on the system? Yes, there's a bunch. The 3 biggest are DesignSafe, Cyverse, and Galaxy. The main Galaxy we have a few petabytes for. All 3 of those use the big systems. They use VMs through Jetstream or Kubernetes, as well as the big machine for alpha data. So, but there's a bunch more. So feel free to reach out.
Thank you so much. And I could do once my baton. Thank you.
Yes.
Then great. Thank you so much. And thank you for the extra effort being in the UK on the street. Yeah, that is fantastic.
Details.
Okay, with this, so the Q&A is open. You can put questions in the chat. You can raise your hand. You can unmute yourself. Any questions to any of the speakers? So I have a question, and I just thought about it, hearing you all talking about it. What do you think about that we offer a gateway showing which of the resources are available? What is, yeah, the measures you presented here, that we show it on a gateway, not like direct access, but something that people can apply and get the forms you have for applications and everything on one page. How would you like that?
Sandra, do you mean for gateway allocation or having sort of a gateways features dashboard kind of thing?
So like a features dashboard where people can see, oh, these are, for example, in Stampede 2 or in Frontera, and so that, because these are fantastic, offers, but it's probably also hard for users to find how to compare it. And so maybe we could put it together. It's like, for example, for smaller system, what are the good jobs for it? For Okami, like, okay, these are the small restrictions, but on the other side, we have, really also space to allow for these jobs. Would that make sense? Would that be something you would be interested in?
I mean, I think all of us showing up here would say that we'd all be happy to put the data in for those kind of thing. It might be best if somebody like SGX or Access Track 2 actually organize the dashboard. Or
yeah,
any of us might be accused of biasing it towards our own systems, but so
yeah, I wanted to say, I think it would be a great task for
everybody, but my guess is we'd all want to put data in if it's such a thing existed.
Yeah, cool. Let me look in the chat whether we have questions. So I think, yeah, it would be great if everyone can agree to that of the speakers. We will contact you and offer them the information on the SGX3. That is cool. So there's a question in the chat. Devin, you won't, yeah, I can read it, but you can also unmute yourself if you feel comfortable with that.
Yeah, sure. Hi, everybody. Thanks for all of those talks. So I'm new to the world of science gateways, but I'm a staff member at the University of Arizona's Research Technologies. And my question is, are there any upcoming events or hackathons that I can attend to learn how to develop a gateway for a site?
So yes, we have hackathons. And we have also our conference where you can learn about different technologies, but really hackathons. We have hackathons, for example, for faculty, also students. So yeah, Claire put it in the chat. Like there's under Science Gateways, faculty hackathon, for example, and we can follow up with you also offline of this call and look at possibilities. Thank you for your interest. Hackathons are really a good idea for learning gateways. So the next question is from Tendai. And you can also unmute yourself if you would like to. Or I can read it. Okay, what be the best resource for viewing, for example, BAM files? If one has many such big files that would be inconvenient to download them to a local computer for viewing, to view them there. So what are good resources for working? So BAM files are in next-gen sequencing, and these are really big files. So any of the resource providers has an idea how to view them online without having to download.
Doing an interactive Galaxy session on JetScreen, or just going to the Galaxy main portal is a good place for BAM in particular. I think Cyverse might have some tools for that too, but Galaxy is the one that springs to mind first.
Okay. Thank you.
One of the things we have under development for Anvil is to make our Scratch visible to science gateways that are hosted on Composable. So I think that would be probably something that can be helpful for cases that mentioned in the question.
Very good. That sounds good. And so there is yeah. So Dan put in the chat there's app development bootcamp also at Tech this summer. So, and there's Cyrus for you know, at UAE. So the ECSS program we just created at all? We don't think so, that NSF took it out. I think there are some approaches to fill it in a different way. So what we, for example, SGX3, what we are offering, for example, is advice. We cannot give really hands-on a lot when it's unpaid. But with me giving this answer, maybe one of the resource provider would like to give an answer on this project. What do you think?
I can jump in there, Sandra. I think that's a fair answer. I think the NSF is trying to build funds into other projects and other opportunities to fill in that need. And of course, the access support team is working to put as many resources available as they can find for the community to fill in some of those holes as well. So no, I don't expect that the ECSS will be resuscitated, but there are a number of things in motion to make up for that.
Thank you so much, Tom. So we are coming to the top of the hour. So maybe we still manage fast to answer one of the questions here. Let me see that. How do host sites handle needs from a science gateway that requires bidirectional communication? If someone wants to jump on that?
Yeah, I think this is Amit. I think Dan responded for TAC also. And I think same thing is true from on our Expanse machine. When a job starts running, you can do connections out of it. I'm pretty sure about that.
Yeah, and same for bridges too. And we can, like, the devil's in the details, obviously. So, we will talk to folks and see exactly what's needed. And yeah, we've done it for a number of gateways. So we could do it again.
And for Jetstream, it's a natural. It's built to communicate both directions. So we actually don't put any restrictions on whatever communications you want to do. So you build your own firewall.
Fantastic. Thank you so much, everyone. This was a great session. Please follow up with us. I would like to follow up with, having maybe this gateway and providing the values for the different infrastructures. Let's work together on that. And with that, thank you to everyone joining, giving the presentations, having the questions. Thanks for all the nice discussions.
Thank you very much.